Hello and welcome. We are into the part 2 of module 3. Here we will be discussing the first order logic, which is basically an elevated version of the propositional logic that we have discussed in the last lecture. So the first order logic is also called FOL, and here, as we have mentioned earlier, we are not going to give a very detailed account of the first order logic, and we'll be happy with just enough of it. So it will be providing us a basic grounding of the logic system that we'll be discussing, or that will be relevant in the semantic web domain, that is to say the description logic. So this will provide a background on that, right? But we will be discussing on the construct of description logic and how it is used in the semantic web domain in detail in different other lecture, right? So to start with, let us look at the power of the propositional logic that we have discussed in the last class. So first of all, the propositional logic is declarative in nature, right? So we can declare the truth value of the sentences, and as the individual sentences, they are conjoined with the other operators, we can create new and complex sentences out of smaller sentences. We can also derive the truth value based on the truth value that we have declared on the basic propositions, right? And the second power or second good point of propositional logic is that propositional logic is compositional. So what we mean by that? So the meaning of the whole can be derived from the meaning of the parts. For example, if you have this sentence like B11 and P12, then the meaning of this can be derived from the meaning of P11 and P12. So for example, if I say that B11 is true and P12 is false, then we can derive this truth value of this sentence to be false, right? Now the other very important feature of propositional logic is that the meaning or the semantics is context independent. So this is very important. So to illustrate this further, so if you have this B11 and say P12, the meaning of B11 will not depend on the meaning of P12. So even if it is happening or this is used in other contexts, for example, or not of say Q11, then the meaning of B1 will be the same as here, right? Or the truth value of B11 will be the same. So the meaning of one part is independent of the context in which it is appearing, right? So, but though it has got these good facilities, but there are certain issues with the propositional logic. So to discuss about those issues, let us try to look at the natural language. So one might have argued that why don't we use natural language for representing knowledge in the computing system? So the first question relating to that is whether we can use natural language as knowledge representation or communication. So we have certain ideas about the word. So is it like we are using natural language to store the representation, or we are using natural language to communicate the ideas that we are having, right? So that is the first question that we need to have. But again, the point where the natural language comes into relevance is that natural language is a very expressive language. You can express almost everything that you have in mind, right? So we need to have a language that will be declarative, like propositional logic, right? So, and on top of that, it should be context independent and unambiguous. If it is ambiguous, if the truth value of a part is depending on in which context it is appearing, then it will be very hard to write an algorithm to process that language. For example, it is very hard to understand the natural language completely by a computing system. Though we have made a fair amount of advancement in understanding natural language through computer programs, but nevertheless there are situations the ambiguities creep in, and the computer programs, they fail to understand the natural languages. But also in quest for this language, apart from having these kind of features like declarative, context independent, ambiguous, it should be more expressive like natural language, right? So this is the other requirement. So what we know that propositional logic basically provide these kind of features like declarative, context independent, or ambiguous, but it is not that expressive like natural language. You cannot really express everything in propositional logic. So we need to have a new language that will have more or less the features of the propositional logic, as well as it will be more expressive and probably more closer to natural language, if not the same, right? So what are the kind of building blocks for this new language? We need to talk about objects. So we know that whenever we communicate our ideas, whenever we store certain piece of knowledge in our mind, we think in terms of the objects. Like Amir Khan is an object, Rani Mukherjee is an object, right? We also relate the objects using certain relationships. For example, Amir Khan and the movie Three Idiots, they are related via this actor relationship. So Amir Khan is an actor in Three Idiots, and Amir Khan is a co-actor of Rani Mukherjee, right? So these are the relations which connects the objects, right? And we can have functions. So the functions, what they do, they accept some objects as parameter and outputs some other objects. For example, if we just put Three Idiots to be the parameter of the function director, they probably will be having as output, say, Raju Hiran, right? So we need to have think in terms of the objects and their relationship, and we can define some function that can map one object to another object. So here I am mapping, in the function part, I am mapping one object to another, right? So let us try to model this sentence like all funny students like comedy movies with propositional logic. So what we need to do in order to capture this, capture the meaning of the sentence, we need to define the proposition for all the students. Like X is a student, Y is a student, Z is a student, X is funny, Y is funny, Z is funny, so on and so forth. Assuming that these are all your students, right? And if you assume that you have got only two movies in your world, so we need to say that M1 is a movie and M2 is a movie by these two propositions, and M1 is a comedy movie. So this is one thing that you have to declare to be true, and M2 is also a comedy movie. That is what you need to declare, right? Now using this, you have to write something like this, like X is a student, X is funny, M1 is a movie, M1 is a comedy. If that is so, then X1 likes M1. That is, the student X like movie M1, right? And you have to write this kind of statement. You see, you have to write these kind of statement for all the other objects or entities that you have in your world, right? So we are stating the similar thing for Y. So this is for X, X M1. So this is for X M1. This is for Y M1. Similarly, we have to write similar statement for z, right, and so on and so forth. And you have to see that you need to see that we are doing this for all the combinations. So and you can perceive that your number of statements to capture this simple statement is going to be very huge, and this is where propositional logic is lacking. So what is the takeaway from this example? The takeaway from this example is that propositional logic is uh, is or propositional logic cannot express general traits with simple constructs. Right. So here we are trying to say that all funny students, right, and they like all the comedy movie, which is kind of implicit here, right? So we need to find some way to capture this, right, and we need to generalize. So which is not present in the propositional logic, right? So let us try to model this. We are making it more complex. All funny students like comedy movies having lead actor as Amir Khan. So what are the important things that are relevant here? So we have objects like Amir Khan, student 1, or it may be student 2, so on and so forth. You have got properties of the relations, like someone is a student, some movie is a comedy movie, someone is funny, and someone likes something, right? You can have functions like lead actor of a movie. So given a movie, who is the lead actor, right? So with this, let us see whether we can represent this statement bit more conveniently, right? So what we can do, we can say that, well, I have a statement. If the statement is so the statement is having one parameter, which is x, right? Now for x, if I say student x, so with that I am asserting that x is a student, right? And by funny x, I am asserting that x is funny. By movie y, I am asserting that y is a movie. And similarly, y is a comedy thing, right? And we are also saying that lead actor of y is Amir Khan. So if all these conditions are satisfied, then we say that x likes y, right? And what is our x? X is a student and y is a movie. So this is exactly what we tried to model, but where this all part is the all part has been modeled? I don't think so. It is not there here, right? So I'm just saying that x is a variable. Now x can be, you can put x anything, like you can put Amir Khan to be x, you can put student to be x, and depending on your current world knowledge, either Amir Khan to be a student can be true or false, or student 1 to be to be true or false. That will depend on your current world knowledge, right? And they will be explicitly stated, like student 1 is a student, right, or student 1 is funny or not, right? But with this, and along with some other constructs, like here I am saying that, so this is a symbol called for all. So by this I am saying for all x, so whatever the value of x can be say Amir Khan, x can be student, x can be 3 idiot, it can be anything. Now if x is a student, so this is the if part of it, right? So from this to this is the if part, right? And this part is the then part, right? So if say I'm putting the value of x to be say student 1, so I'm saying if student 1 is a student, student 1 is funny, and why to be say movie 1? Movie 1 is so M1 is a movie, M1 is comedy, and lead actor of M1 is Amir Khan. Then student 1 likes M1, right? Now you can see that we can put any values to x, any value to y, and kind of encode the huge number of rules that we had to write in order to model this in propositional logic in a single statement. So it is a very concise way to represent the similar thing that we have done in propositional logic. So in propositional logic we are kind of flattening out the thing. Here we are putting all these statements in a template kind of statement. So this is a kind of template, right? And in this template you have got these variables, and you assign the values to the variables, you get individual statements, right? So this is the power of the new language that we are going to talk about, which is the first order logic, right? So coming to the mathematical model of the first order logic. So when we say that so here I am just presenting a scenario, then I will go to the mathematical model. So you have got Richard and John, right? So Richard the Lionheart and King John, right? Now this Richard is a kind of person, right? And John is a kind of person as well as a king, right? And Richard, as being a king, he has a crown, he has got something on his head. Now you can see that on head is a relation, and that particular thing is a crown, right? And John is a brother of Richard, and Richard is a brother of John, and Richard has a left leg, so this is basically Richard's left leg, and this is the left leg of John, which is John's left leg, right? Now how do we represent this person? So the person, it will be a kind of set, right? So what kind of thing we are trying to say? Person X. So this means that it is a kind of set which is containing all the individuals that are of type person, right? Now how do you model a relation like this? How do you model? So you can see that we can model these kind of constructs which are having only one parameter to be a set, right? So in mathematically we can represent that as a set. Now let us try to represent, say, this brother relationship, right? So this brother relationship basically can be represented as a set of tuples, right? So it is represented again as a set. So this relation can be represented as a set which is a set of tuples. And what will this tuple contain? These tuple will contain the entities that are related to each other via a particular relationship. Now if you say that if you see this brotherhood relationship, so brother, in brother I can say that Richard is a brother of John and John is a brother of Richard. So these are the two tuples that are member of the relation set brother, right? So likewise we can we can write what would be the set for this on head relationship. So for this on head relation, the set would be say John is having something, say C1, which is a crown, right? So this is what we can say, right? So on head I think the directionality will be different, so we should write C1 John instead of John C1, because the directionality is from crown to head. And on and also we can say that the set crown will contain C1. Or again, it can contain many things, but in order to make this model to be true, make this scenario to be true, C1 should be a member of the set ground, right? So you can see that Crown King John is a relation, King John Richard Lionheart is a relation, and Richard Lionheart and King John, they are also forming relation, right? So basically relation is a set. So this is again we are representing almost everything as set. So it is a set of tuples that are related, right? Now coming to function, basically here the example is the left leg. So what it is doing, it is taking as argument the one object like Richard, and what would be the value of that? The value would be the left leg of Richard. So for this function, if you put King John to be the input, the output would be John's left leg, right? So what it is basically doing, as I have mentioned earlier, it is a mapping of set of objects to another set of objects, right? So here we are mapping the set of persons. So this is the person set to the set of, say, left legs, right? And one thing that we need to consider, that these functions are total functions. So that means for every element in the first set will have a mapped entity in the maps, right? So you don't have any entity which is left behind. So every entity will have a mapping. So this is called a total function. So by this logic, you can say that Crown will also be having a left leg, because I will not say person, I will say you can think of any all the elements in this domain, right? So if you assume that to be a set, right? So you have all the objects, right? Now in that logic, the Crown itself will be having a left leg, or the left leg, which is also an entity or object in this domain, will also have a left leg. So that's why it's a total function. Now going to the syntax, again this is the grammar of the first order logic. So the most basic entities in this grammar are the terms, right? So the term can be a function, and you can see that function has got arguments. It can have multiple arguments. We have already given an example of a function like, say, lead actor, which expects one argument here, right? It can be a constant, like, say, we say that this was equal to Amir Khan, right? So lead actor of, say, Three Idiot is Amir Khan. So this Amir Khan is a constant, or it can be a variable also. So you can say that lead actor is something, say, X, right? And X can be anything, right? It can be variable. Now the atomic sentence can either be a predicate. We have already given the example of a predicate, like, say, brother, say X, Y. So X is a brother of Y, right? So again, these are terms, right? And by the definition, the term can be a constant, the term can be a variable, term can be a function also, right? And another atomic sentence you can write, that is term equal to term, example of which we have already given, right? So this is an example of an atomic sentence which is belonging to this term equal to term atomic template, right? Now a sentence can be an atomic sentence, or it can be two sentences connected via a connective, and the connectives we know already, the forward implication, the both way implication, logical and logical or, right? So another kind of sentence one can write is the quantifier followed by a set of variables and then a sentence. So the example of which we have already given. So this is an example of a quantifier. So for example, for all x, for all y, you have written like student x, so on and so forth, right? So you see that this is your quantifier, this is your quantifier, these are your variables, and this is a sentence, right? And then sentence can be a sentence like these or these or these also, right? So we'll talk about nested quantifier later, right? Or a sentence can be negated to flip its truth value. So one point that I forgot to mention, that this predicate, the value of the predicate can either be true or false, right? So John is a brother of Richard, that is true, but John is a brother of Mary, or John is a brother of, say, Abraham Lincoln, is not, may not be true, right? Now this quantifier can be two. One is for all, so it will be true if for all the values of something the sentence holds. So we will try to talk about the detailed meaning of this for all in the future slides. And the other kind of quantifier is called the existential quantifier. So this for all is also called the universal quantifier, at this is called there exists, and this there exists is called existential quantifier. So this asserts that at least for one instance of the variable, certain sentence should be true, right? So that is what it tries to impose, right? We'll see the use of these two quantifiers later, right? The constant can be anything, like you can name anything like Crown, John, etc., etc. The variable, again, you can name anything. The predicate, they have got names like before, has, color, brother, etc. The function, again, they have their names like mother, left leg, color. Depending on the kind of application domain you are working in, you have different symbols to represent the predicates and the function, variables, constants, right? And of course there are precedence relationship between these operators. So as you can see that for all is will be processed first, then there exists, then negation, then your logical and, logical or followed by the forward implication, and then both way implication. Now let us try to, this predicates and function, visually they look to be same. They have a symbol which is the predicate of the function name, and they have a set of arguments, right? So both of them look like same, but in a semantic term they are different. So let us see what are the differences between predicates and function. So the predicates, they basically establish relationship between different objects. It can be between two objects. So if it is between two objects, then we say binary relationship. So it can have also multiple objects. So multiple objects, they can be related with each other in a single predicate. So the input to this to the predicates are the objects, and the output is a truth value, whether the relation holds or not, right? So if it holds, then true, the output would be true. If it is not, then the output will be false, right? So let us see now what are the functions. So functions are not really relations, they are mapping from one object to another object, right? So the input to the functions again is similar, they are objects, but the output is an object, right? So let us try to see some examples. So before going to the examples, let us talk about the differences more. So you can think this predicate to be functions, but with the Boolean output. So they only output Boolean values, but there are more to this. These predicates, they combine the symbols, like they take the arguments and make an atomic sentence, but the functions, they cannot make an atomic sentence, right? So as we have talked about earlier, that a sentence must have a truth value, right? But a function does not have a truth value. The function, they can output something which is an object again, but the predicates, they output truth value, right? So it can be true or false under a given scenario, right? Now the functions, they also combine symbols, but what they form really the terms, right? So the terms, basically, what are those? They are kind of expressions which refer to the objects, right? So for example, the lead actor of, say, Three Idiots. So it is a term, but it is not an atomic sentence. So this lead actor of Three Idiots has got a distinct value as an object, but it is not having a truth value, right? Let us take some examples to clarify the notions more. So the examples of the predicates are like Three Idiots has actor like Amir Khan. So it is said to be true, right? So this actor is a predicate now. Now 14th August is a holiday which is false. President of USA is Donald Trump is true. Now you can see that either we are saying that the construct is true, the sentence is true, or sentence is false. But in function, what are we doing? So we are taking an example like sitting next to. So we have student 1 who is sitting next to student 1, which is basically student 2. So here we are not really putting having a truth value as the outcome. See, now here one point that I will also like to mention, that you can represent a predicate as a function as well. So here you can see that we are representing the same piece of knowledge or information in function form. So we express that in predicate form, but the same piece of knowledge we are expressing as the function form. So here I am saying the president of USA, and it is mapping to the object Donald Trump. So you can see that we can represent the same fact either in predicate or function. Again, it is a design choice. So there are certain algorithms, they work better if you do not have any function. So it is a kind of choice of the application developer, the algorithm developer, what kind of constructs they will be using, right? Now coming to the atomic sentences, so what are the kind of atomic sentences we can have? So as we have mentioned earlier, the predicates, they are atomic, right? You are having a truth value to it, or the form like term 1 equal to term 2. It is also kind of predicate. You can see that the equality is a predicate that can either output true or false, right? But it is looking differently than predicate, but more or less semantically they are the same. The terms can be a function, as here we can put a function in place of term 1, or it can be a constant, or it can be a variable. Quantifier. So these are the most important elements in first order logic, right? So as we have mentioned that we have two kinds of quantifiers, let us talk about the universal quantifiers first. So how do we represent something like all kids like ice cream? So as you see that we are trying to do it, we are trying to impose, we are trying to say this for all the kids in the world, right? So it is universal. The statement should be universal. So as this is universal, we should use the universal quantifiers, right? Now let us try to see what are the kind of predicates that we can think of. Now So we are saying that we'll be using universal quantifier, right? Now I'm presenting this it like this. See, if something is a kid and something else is an ice cream, then the first thing will like the second thing, right? So this is how we are going, right? So I'm saying that something, sorry, we are saying that something is a kid. So kid X and something is an ice cream, and that will be say Y, right? And they should be both true. If this is so, then we can say that likes X, Y, right? So these are variables. This X can be any kid around the world. This Y can be any ice cream around the world. So we are doing it for any X and any Y. So this will read like, for all X, Y, kid X and ice cream Y implies X likes Y, right? So let us take another example from the Impus book. The squares neighboring the impulse is melee. So this is a rule that is true, right? So how do we represent this? So we need to take at least two squares to represent this. So let us have two squares now. So square X and square Y, right? Now also I need to say that these two squares are neighbor to each other, right? B O. So X is a neighbor of Y, right? Of course, one of them should be having the impulse to smell the the to smell it from the other neighboring square. So we should write, say something like this. Say you have impulse in, say, Y, right? So in that case, your X will be smelly. And we are doing it for all the squares, right? So you have to say X, Y, right? So while we are stating some general property, so this is where we started when we are discussing the drawbacks of the propositional logic. We can generalize, right? So whenever we are stating some general properties, then we use the universal quantification. And the form of the universal quantification is for all X, the P should be true. This P is a sentence that will have the mention of this variable, right? So this is universal quantifier. Now let us talk about this universal quantifier. There are certain other caveats, or there are certain other subtleties of using this universal quantifier. Basically, when we are trying to interpret the meaning of universal quantifier. So this is what we are saying. So we need to check whether this is true or not, right? So this is true. So this is what we are asserting, and we'll be providing example for this. So it this for all X P is true when P is true for all the extended interpretations. So we have talked about many things, but without explaining this, let us take an example to illustrate this, right? So let us take the sentence like all kings are persons, right? So we can easily represent this in a form of in first order logic. Basically, for all X, king X implies person X, right? Now you know that in the when we talked about the example of Richard and John, there are many objects in the current world, right? So what are the objects? These objects can be Richard, it can be King John, it can be Richard's left leg, it can be John's left leg, and it can be crown, right? So this X can be anything. So while you are writing an algorithm to process to understand the meaning of this, it is not like you will be saying that only X is Richard is a king or a John is a king, because that is what you are trying to define. But the point that I am trying to make here, that X can be instantiated by any of these values, right? Now if we put this and flatten the statements, there will be 1 2 3 4 5 statements, right? Richard is a king, so you are putting X to be Richard. I'm saying Richard is a king, then Richard is a person. King John is a king, implies King John is a person. Richard's left leg is a king, implies Richard's left leg is a person. So we see that we are doing it for all the values of the variable, but out of them only one interpretation is intended by the domain. So we know that it is true for only King John, but for the others it is not, doesn't really matter. But the point is, in the logic sense, this should also be true, this should be true, this should be true, this should be true, and this should be true. So these all are called the extended interpretation. Extended interpretation, and this is called the intended interpretation. Now look at the extended interpretations. We know that the crown is not a king. And what is the semantics of one implication? So this is your P, this is your key Q. So we can flatten this out like not P or Q. Now you know that P is false, right? Now if P is false, this whole statement will become to be true. And you take this. So here P is true and Q is true. So that's why P implies Q would be true. So this statement is true for the intended interpretation and as well as all the extended interpretations, right? So this is how we can understand the meaning of the universal quantifier, right? But there are some caveats. So many a times it is seen that people try to model all kings are persons, like for all king X and person X. So this is a very common mistake people generally make, and you need to be very careful about this. And I'll tell why this kind of representation is not really related to this particular statement. So in order to make it to be true, every element like Richard King John, Richard's left leg, John's left leg, crown, they have to be king and they have to be person, all of them. Then only this statement will be true, which is not really what we are trying to model. So it is a very generic notion that whenever you have got for all, then it should be coupled with implication. So these two goes together. So this is a very important thing that you need to remember when you are modeling something in with universal quantifier, right? So we'll talk about the semantics of the Existential Quantifier. So here you have a statement like this: King John has a crown on his head. So we are reinterpreting the sentence like this, that there is at least something, at least one thing which is on King John's or John's head, and that is a crown, right? Now one again this is another modeling error that sometimes people couple their exist with implication, right, which doesn't really go together. So you can see that if I say whenever something is a crown, that is that implies that X is John's head. Now X can be say you can say John, right? X can be John. Now what it is coming up to be? Crown John implies on head John John, right? So this is false, of course, because John is not a crown, but we'll end up with inferring that John is on John's head, right? Which is a kind of thing that we don't want to model, right? So the other word of caution or the point to ponder that there exists X will always will always come with the logical end. They go together. So with this, I'll stop here. In the next lecture, next part of this video, we'll talk about how do we nest the quantifiers to express more complex ideas. Thank you very much.